In this example, we want to solve the following nonlinear system of equations, which is given below over here. And the methods that we've discussed so far are things like elimination and substitution. And so if we first just think about strategies for solving this, if we want to use elimination, then we need to have the same power of x or y appear in both equations, because I can eliminate one of the variables by multiplying one or both equations by constants and then adding and subtracting those equations. So the powers of y are different in the top and bottom equation. The powers of x are different. So the elimination method doesn't seem like it's going to work very easily or at all. But that means we can try the substitution. And the substitution method says if we can solve for one of the variables in some fashion and substitute that into the second equation, then we would get an equation in one variable that we could try and solve. So one thing to try here is we can think about solving the top equation for y, since that should be a pretty quick process. So doing substitution, we could take the top equation and solve for y, and that would give y is equal to the square root of x minus 2. And then we can substitute this in place of y in the second equation. So in the second equation, we have 2x squared plus y squared. And now we could replace y with the relation we found in equation 1, which was y is equal to the square root of x minus 2. And this is equal to 1. And that means we have 2x squared, and then squaring the square root of x minus 2 would give us x minus 2. We set that equal to 1. So we have a quadratic equation. Let's bring everything to the same side of the equation by subtracting 1. And now we could use the quadratic formula, or we can try and factor this. And in fact, this quadratic does factor into factors 2x plus 3 and x minus 1. And if you can't see how to factor it very easily, recall you could always use the quadratic formula. And from the first factor, we see that one solution is x is minus 3 halves. And from the second factor, we get the solution that x is equal to 1. And now we could take each of these solutions and try and figure out what the corresponding y value is by plugging them in to the relation we got from the first equation. But here, notice this is a square root, and we need to be careful with square roots in that we can't take the square root of a negative number. So what that means is that y is only going to be defined if x minus 2 is greater than or equal to 0, which means y is only going to be defined if x is greater than or equal to 2. And for both of these potential values, they're both less than 2. So at both of these values, minus 3 halves and 1 for x, y is undefined. So what we've observed so far is that if we find solutions to these equations, the values of x are going to have to be either minus 3 halves or 1. And in either of those cases, there is no corresponding value of y, since y is undefined at those values. So this means this system has no solution, okay? And so just like linear systems that we worked with, not every system of equations has a solution. And so we just found out that this one doesn't. And we could have solved this using other substitutions. So if it's not clear what to do, you can try doing different things. In equation 2, the only things that would probably be very simple to solve for would be either x squared or y squared. And we can't really plug those in anywhere in the top equation. So that might take a little bit of work to get that sort of substitution to work. And we could have tried to solve for x up here, and we definitely could. But again, that might require a little bit more work than solving for y, which we were able to do most immediately. And lastly, let's just see what the corresponding picture, the graph, to go along with this system would look like. So just to sketch this informally over here, the top equation, graph that one in red, y is equal to the square root of x minus 2. If you know what the square root function looks like, this would be the square root of x that shifted over to the right 2 units. So it would look like this. Okay, and recall the domain of this was x is bigger than or equal to 2. So it makes sense that the graph doesn't begin until we hit x equals 2. And if you don't know offhand what the graph of the square root of x looks like, and transformations wouldn't help you then, recall you can always just make a chart to plot a couple of values and then connect the dots. And so just showing what that would look like here, we could connect these points and that would give us the same curve, or it's fine to use technology if you have that available. The other graph, 2x squared plus y squared equals 1. This is going to be an ellipse. So it sort of looks like a circle, but we have different coefficients in front of the x squared and y squared. So we're going to get an ellipse for that. And we could identify a couple of key points here, such as the x-intercept for that graph by setting y equal to 0 and solving for x, which would give us 2x squared is equal to 1. So x squared is equal to 1/2. And this gives us x-intercepts at square root of 1/2, 0, and minus the square root of 1/2, 0. So we can mark that over here and here, and we can similarly find the y-intercepts by setting x equal to 0, which would give us 0 squared plus y squared is equal to 1, and that would give us y-intercepts at 0, 1, and 0 minus 1. So that would be, say, over here and over here. So we get an ellipse for the second graph. And what's important to note here is that we're going to get solutions at points where these two curves intersect, and there are no intersection points. So that matches up with our result that there was no solution to this system.